Alright, hi everybody, we're here. Welcome back to Chapter 3. I mean, Chem 161. It's really just Chapter 3 again. What do we got coming up? So we have lab worksheet number 3 due on Wednesday the 18th. Closes on Thursday, so make sure you get that in before then. It is about Beer's Law. Beer's Law is one of those topics that's really important for chemical and analysis. It's a spectroscopic technique that we care about. And I've never seen it taught in any class other than the lab. Like, it's purely just a lab thing. It's not terribly difficult. It's a very linear, simple equation. I've been getting a few questions about it, but not too many. So if everything is going great, then hooray. Otherwise, if you have any questions about it, let me know in the class Discord, because that's where I'll be happy to answer them. So we're going to continue our discussion on some periodic trends that are going to be based on quantum mechanical properties. So we've basically discussed everything we can about electrons, like where they live, all about quantum numbers. There are a few things that we're going to touch on in chapters 4 and 5. But now what we're going to do is we're going to look at some properties of atoms that are affected by things like energy and where the electrons are and so on and so forth. So the first thing we want to talk about is radius. How big are atoms? And we said last week that there were two factors that we were going to care about. And so the first factor here was how many energy levels there are that have electrons. So that's going to be n. What's the highest n? That's going to affect our result of how big an atom is. And then the effective nuclear charge, which we talked a little bit about, where I drew a diagram of, like, here's the nucleus, here's some electrons flying around. If I'm an electron out here, these electrons are attracted to the nucleus, and so is this one. But these electrons push it away. And as a result, what I feel out here is going to be reduced by the electrons that are in the way. So Z effective was the atomic number minus the number of shielding electrons, or in other words, any core electrons. We're going to subtract those out. All right. Now, this is a diagram of, on the x-axis we have atomic number, so that's Z. And then on the y-axis we have the radius of the atom in picometers. And you can see here that there's a lot of this going on. It's really high and then it starts to taper off and then this sort of thing is going on over and over and over and over again. What we're going to try and do is we're going to try and explain this. So we're going to come back to this diagram as we do the explanation. So the first feature that we're going to talk about is what is the impact of the not the atomic number, but the shell number n. As n gets bigger, what happens? So let's think about that for a second as we do a discussion. So the first thing we want to talk about is that electrons in general don't follow classical mechanics. So it's very hard to predict where they are at any given time. But on average, they follow patterns that we can model. And even with the ambiguity that electrons provide with where they can move and how fast they're going and whatever, there is a fundamental principle that is true. Electrons are always attracted to the nucleus because they are oppositely charged from the nucleus. So as a result, they will remain, on average, a fixed distance away based on their quantum numbers, n, l, m sub l, and m sub s. We can use this equation, which is not appearing here. Why is it not working? Oh, because I'm clicking on something totally different. That's why. We can use this equation here to help us figure out how electrons behave. This is called Coulomb's law. And you're probably looking at this and going, I thought we weren't doing any more math. In fact, why is the calculator even showing? Well, don't worry about that. I forgot to cover it up. That's why. And it's true. We're not going to follow any math. I'm writing these numbers on the screen. Oops. just in case you're curious, if you want to know what epsilon naught was or whatever. But in reality, we don't care about these numbers. Nobody cares. We're just going to cross them out. We're going to replace this equal sign with this. This symbol means proportional. Something is proportional when there is a constant that relates it to something else. So the energy of attraction between two charged objects is going to be proportional to whatever the magnitude is of the charges and the distance between those objects. Now, these units are going to be in coulombs, so charge is measured in coulombs, and radius is measured in meters. We talked about what a coulomb is when we talked about Millikan's oil drop experiment. You probably have forgotten what that was and don't give a shit. And I can't blame you. But the whole point of us talking about the Millikan experiment was that electrons have charge, and that charge is equal to 1.609 times 10 to the minus 19 coulombs. Now, for our purposes, we're just going to represent charge as like plus, minus, -2, +2, whatever. And then R will just will abstract into, oh, it's bigger or smaller. All right, so what can we do with this? Well, the first thing that we want to do is we want to explore this formula a little bit in terms of charge. If I have two things that are oppositely charged, and I multiply them together, the result is a negative number, right? And then, whether I have positive or negative, if I multiply two with the same charge together, I get a positive number. So, if I get a negative result for E, then I have an attraction. And if I have a positive result for E, I have a repulsion. So what we're going to do is we're going to play with these variables and see what the impact is on E. Do I make E bigger or smaller? And if I know what the impact is on E, then I can explain things like, okay, where's my electron? So let's do that. If I have multiple electrons around nucleus, these factors come into play. All electrons are attracted to the nucleus, and all electrons repel each other. And so this is going to go into that diagram that I drew on Thursday last week, where I had a bunch of protons in the nucleus and electrons that were core electrons pushing away valence electrons. And so that's going to look like this. So we're going to calculate the effect of Z effective nuclear charge, in this manner. What's the atomic number? And then we're going to subtract the number of core electrons. So here I would have, as our example here, Z effective would be, there are 3 protons, and I have 2 core electrons. Or in other words, this is the charge that my valence electron on lithium feels. So you can calculate Z effective for any element by writing its electron configuration. So for lithium, that would just be this, circling the valence electrons and then underlining the core electrons and going, okay, how many core electrons are there? And that's how I get this number. And you can do this for anything on the periodic table now, because we've done electron configurations. And I need to check it. I want to make sure that you have an example or two to calculate Z effective for these. Yeah, you do. Okay. All right. So what I want you to do is, using this formula, I want you to tell me what is Z effective for a chlorine atom. So start by writing out the electron configuration on your paper. Determine how many valence electrons there are, determine how many core electrons there are, and then compute the calculation. We'll put the formula on the screen here. So Z effective is Z minus core electrons. All right, I'll give you a few minutes to calculate that. Write the number first and then the sign in the chat. Hint, it should be a positive number because it's Z, right? All right, see you in a bit. All right, one more minute to get your answer in. All right, let's go over the answer here. So first, we're going to write out the electron configuration for chlorine. And so that's going to be, I'm going to write the whole thing out, just to make it easier. All right, so there we go. I'm going to circle my valence electrons, so that's n equals 3. I'm going to underline my core electrons. So we're going to subtract these two. So what number of protons is in chlorine? That's 17. And then I'm going to subtract the number of core electrons. So that would be 6, 8, 10. There you go. All right, that's okay. You have a chance to redeem yourself. Let's do this for boron. I'll give you another minute to do it. All right, we'll do the same calculation. So I'm going to put it a little further down here. All right, so we should be able to write those out really quickly. Here are my valence electrons. Here are my core electrons. Z effective is number of protons, so boron is 5, minus the number of core electrons, that's these two. And there you go, very good. Z effective should always be a positive number because you can't have more electrons than protons. Not in a neutral element, anyway. And you certainly will never have more core electrons than protons because you have to have some electrons on the valence layer, right? All right. Do we have another one here? No, we don't. Okay. We'll calculate the Z effective for a transition metal in a little bit, actually. All right. So with this in mind, this calculation is going to be super important. We're going to use Z effective for the remainder of today's lecture, and all quantum mechanical effects use Z effective. So know how to calculate Z effective because it's going to be very relevant. All right. Now we can use Z effective to figure out how big are atoms. So we're going to go over here, and I need to actually capture this part on the screen here. And I have the wrong thing booted up, so hold on. So we will open the Electron config. Boop, there we go. All right, so down here at the bottom is our nucleus. Give me just a second. I want to make sure that I'm... Okay, cool. Down here at the bottom is our nucleus. Here's n equals 1. Here's n equals 2. Here's n equals 3. Which electrons are further? Well, if I have something that only has electrons in n equals 1, it's only going to be this big, right? But if I have something that's in n equals 2, it's going to be this big. So, our conclusion that we get to is bigger n equals larger atomic radius. And that should be very apparent. Oh, my electrons are further away. They have to be. I can't cram that many electrons in a tiny space because they all repel each other, right? Therefore, the more electrons that I have that fill more shells, the bigger my atom gets. Cool, we can understand that part. That's trivial. Now, the issue arises when I'm comparing things like, say, this atom, which would be 10, 11, 12, 13. So this would be aluminum. What if I was comparing something like aluminum to, say, silicon? Well, now my electrons are at roughly the same distance, right? So if everything is in the n equals 3 area, then the next step is to use the effective. So if you are comparing two atoms that have the same n, the next thing that you're going to use is the effective to compare their size. And the way that that works is like this. We're going to go back over here. Let's suppose that I have two atoms that have the same n. So we're going to look at silicon and aluminum. And you're going to notice why I stopped there. Because work smarter, not harder. Right? There's our electron configurations. I'm going to circle the core electron, or I'm going to circle the valence electrons on both of these. We're going to underline the core electrons. And then we'll calculate Z effective. So for silicon, silicon is element number 14. And there are 10 valence electrons. For aluminum, I have 13 protons in the nucleus, and I still have 10 valence electrons. And so these are our Z effectives. For silicon, we get 4. And for aluminum, we get 3. Okay, let's go back over here. And I'm going to get rid of all of this over here, so it's just not in the way. But I'm going to draw a smaller cartoon of this. Not with the select tool, but... So here are my electrons in n equals 3 for aluminum. And then, so this is aluminum. And then down here we'll do the same thing for silicon. Oop, not n equals 4, sorry. And I have S electrons in here too, but I forgot those. That's okay. All right. What electrons or what's going to happen to the effect of these electrons being pulled in? What is going to have the better pull? Z effective of 3 or 4? Remember, all those electrons are roughly the same distance. Which will attract them to the nucleus more strongly? And the answer is, of course, well, the bigger Z effective is a stronger pull, right? And the effect of that is the bigger Z effective is, the smaller the radius of the atom. Because it's pulling those electrons harder. Doesn't matter that it's pulling more of them. The force each electron feels is +4. Because valence electrons don't really repel each other outward, right? Only the core electrons will push the electrons away. The valence electrons sort of only push each other laterally. So the main attractive force is going to be the nucleus. And if there's an effective nuclear charge of 4 versus 3, the atom will the nucleus will pull those electrons in that much harder. So those are our consequences of quantum mechanics, and we'll summarize them on this slide here. If you're comparing atoms with different n levels, the larger n is the larger atom. And the smaller n is the smaller atom. And this is always from the perspective of radius here. But if we're looking at the same n, the bigger Z effective is, the more force pulls those electrons in the valence layer towards the nucleus, and that makes it smaller. Smaller atoms have smaller Z effective is a bigger atom, because the electrons are not pulled as tightly by the force of fewer effective protons. And let's go back and look at this diagram and see if we can reconcile everything that we just talked about. And so you'll notice that every time we move from one end to another, there's a huge jump. So as I increase n, so this is n equals 2. Oh, for fuck's sake. I hate PowerPoint for some reason. It doesn't like my tablet. There we go. This is n equals 3. I had to write real slow or else it freaks out. And so on and so forth. And you can see each time we add a new n, the radius gets bigger and bigger and bigger and bigger. Now, if we're looking within an n, so within n equals 2 here, so that would be this set right here, we have Z effective of 1, 2, 3, 4, 5, And you can see that, generally speaking, as we increase Z effective, the atoms get smaller and smaller and smaller. And that's because the same distance, roughly, of electrons, all of them in the n equals 2 region, are getting pulled by more and more effective protons. Within n equals 2, all of the core electron count remains the same. It's always 2, right? Now, an interesting thing happens in here, and also here, where we get kind of weird effects going on. And what ends up happening here is that in these regions, you get 2 over and over and over and over for Z effective. And we're going to show that on here because I don't want to draw on this image anymore. For whatever reason, drawing on pictures makes PowerPoint freak out. So let's go back over here. And I'm going to pick Z effective for 2 elements. And let me grab my periodic table here. So I pick 2 elements that don't have exceptions to them. So we're going to look at vanadium and chromium. So first, let's do the electron configuration for vanadium. So that would be, we're going to just shortcut this. Argon, 4s2, 3d, 3. And for chromium, that would also be argon, 4s. Oh, the graph is covering vanadium. Thank you. Yeah, let's fix that. 2, 3d, 4. All right. And in argon, there are 18 electrons. We'll just write that down here. So let's underline the core electrons and circle the valence electrons. So here's my valence, and then here's my core. And you'll notice that this is the part where I told you that I want you to do this other than what the book is doing. Because the book would count these as valence electrons. We're going to count them as core electrons for this purpose. So that when we calculate the effective here, well, vanadium is element 23, and I'm going to subtract all the core electrons from it. And I'm going to do the same thing for chromium here. Well, that's 24, but there are now 22 electrons. And the effect that we observe is that for transition metals, they're all roughly the same size. And wouldn't you know it, when you look at this diagram right here, what happens in this region right here? They don't really seem to change all that much. In fact, some of them go up. Now, on the right, in the period 5 transition elements, it's a lot more exaggerated. But you could still say that, okay, yeah, if I took the average, they're kind of roughly in like this region right here, right? So for our purposes, we're going to just say, okay, well, Z effective governs the radius within a given n. Now, how do we deal with the nuances? The nuances are a little bit more difficult to explain, and the reason for that is because the calculation of Z effective is much, much more complicated than what I am actually giving you for this class. So Z effective being written as atomic number minus the number of core electrons is very simple, and it works best for elements in groups 1, 2, and then 13 through 18. In other words, not transition metals. If you want to calculate Z effective for transition metals, there is a set of rules. It's called Slater's rules, and this is an inorganic thing where instead of counting a d electron as a whole shielding electron, we count it as part of a shielding electron. And even s electrons in the valence layer count as partial shielding electrons. And so you have to like calculate, okay, what is each type of electron? What shell is it in? Is it s, p, d, or f? And then you multiply by a multiplier, and you get a fraction. And if you calculate z effective that way, you get this finer detail that you observe in this region. For our purposes, that's too much work for an introductory class. This is technically an introductory class. It might not feel like it, but it sure is. The rabbit hole for this goes real deep. For our purposes, we're just going to use, okay, if you get z effective and it's the same, then it's going to mean that the atoms are roughly the same size. So if on an exam I asked you, tell me why are all the transition metals roughly the same size, the answer would be they're all in the same N, and they have the same Z effective. For other elements that are not transition metals, so oops, I'm writing on the periodic table here. So like over here in n equals 3, you can see this just plummets. There is no region in here where it looks like anything is roughly the same size. Everything just drops. And if you exclude the transition metals, that trend tends to be constant. There are some oddities and exceptions, of course, because there always is. But for our purposes, using this just count Z effective as 2 for transition metals helps us explain this well enough to get by. All right, we can get out of this screen now, so let's go back to where we were. All right, so there's your summary for atomic size. And that's quantum mechanics in one slide right there. If there is an important slide in Chapter 3, it is literally what I've written in red on this screen. If n differs, bigger n is larger atom, smaller n is smaller atom by radius. If n is the same, look at Z effective, bigger Z effective, smaller atom. Smaller Z effective, bigger atom. Congratulations. We could have done Chapter 3 in like 90 seconds. I could just write this on the screen and be like, you're done. That's all we care about. That's literally Chapter 3. That is literally quantum mechanics is right there. However, in order to understand what n and Z effective are, we had to do all this bullshit. So sorry for wasting 3 weeks of your life in this class, I guess. All right, I hope you write it down because now it's gone. You can never rewind the video. You can never pause. You can never look this up on Wikipedia. And I mean, it's all there, but all right. Now, this is just a discussion. We haven't talked about ionization energy. We're going to come back to that in a little bit. Actually, I'm going to come back to this discussion later. So, there's our summary. Okay. I'm going to talk about ionization energy next, so I'm going to come back to these slides and we'll talk about that then. All right. So let's do an example. I'm going to compare lithium and beryllium. And so I want you to first calculate Z effective for each atom. And then I want you to make a little chart that looks like this. So here's our atoms that we're going to look at. And I want you to do something like this. N, so whatever the highest N is, and then whatever Z effective is. So fill in this chart for these two atoms, and then I want you to tell me which atom is the smaller atom. Okay? I'm going to give you 2 or 3 minutes to do that, and we'll go over the answers in a second. All right, I had to go get some more water. So, all right, let's go over the answers. So, first, in order to do this, you do have to write out the electron configurations. Although after a while, you can stop doing this because you'll know the answers. Like you know, oh, okay, lithium's in the second row, so this must be true. So, duh. N equals 2. Calculating Z effective might be a little more difficult without the electron configurations. But we know that for lithium, it's got 3 protons, and it's got 2 core electrons. So there we go. And then we can do Z effective for beryllium. Got 4 protons, still has 2 core electrons, so there you go. And then now you just have to look at your chart. Okay, which atom is bigger? Well, we'd look at N. Oh, they're the same N, so now we go over to the next column. Okay, which atom has the bigger Z effective? That'll be the smaller atom. And so here you go. Oops, I don't know what I just hit, but there we go. Huzzah! There you go. All right. So whenever I asked you which atom is bigger or smaller by atomic radius, draw out a chart just like this. You'll get the right answer every time. All right. Let's do another one. I'm going to erase this. Which atom is bigger? Oxygen or nitrogen? Make your chart. In fact, if you follow this algorithm, the hardest part of these questions is going to be this. Which word did I use? Because sometimes I'll ask you for the smaller atom, and sometimes I'll ask you for the bigger one. So don't do everything right and then put the wrong thing down because you're used to me saying which is smaller. So be careful. All right, one more minute. We'll go over the answer. All right, let's make our little chart here. So I'm going to go... I realized I could just make the chart look a little cleaner by doing it this way. All right, so oxygen and nitrogen, they're both N equals 2, right? Eight? 6, 8? Yeah, there we go. And then nitrogen... I really should just have the periodic table, like, push pinned to my wall here. I have a space for it. I should do that. All right, so there's what we got. So what's the effective for each of these? So here are my core electrons. We'll underline those. So 8 protons minus 2 core electrons is 6 plus. And then 7 protons of nitrogen minus the 2 core electrons is 5 plus. Yeah, be careful. You only want the core electrons. There you go. You have the right numbers now. And so I want the bigger atom. So if I want a bigger atom, I want the smaller Z effective. All right, there you go. That's atomic size. So now, if I give you any pair of atoms, you should be able to tell me which one is bigger based on these trends. Now, what I'm not going to do is I'm not going to give you... If we go back to this diagram here. I'm not going to give you 2 transition metals, because that's too hard. It's impossible for you to know. I'm also not going to give you 2 elements that are too far apart. So, for example, I would not ask you to compare sodium with whatever the hell this is. I don't know what that is. What did I just circle? What's next to cesium here? That's like not even... That's like lanthanum. Like, who gives a shit, right? Like, that's too hard. Those are too far apart. So I will only test you on adjacent, I don't know how to spell adjacent, atoms on the periodic table. Or atoms in the same row / column. So if I gave you a periodic table, I might say, okay, I'm going to compare sodium with phosphorus. No, that's silicon, sorry. You could do that comparison because they have the same N but different Z effective. Or I could say compare sodium with rubidium. That would also be doable because you could say, oh, well, it's rubidium. It has a bigger N. And then you're done. If I change both variables on you, it gets difficult. Now, I can't do diagonal. Actually, now that I think about this, I should just scribble this part out. This is really... This right here is the stipulation. I can only pick atoms that are in the same row or the same column. If you do diagonal, you get weird things going on because comparing them both in one diagonal direction, it's super obvious because it's the one with the bigger N. And then if you have a bigger N and smaller Z effective, duh. But what if you have bigger N and then a bigger Z effective? And then it becomes it's ambiguous. So I'm not going to give you diagonals. There might be an example in here that I've put purposely so we can have that conversation. But I'm not going to actually do that on a test. So let me clear this real quick so you can read it. All right. So everything we talked about for this so far has been a neutral atom. What happens if we have an ion? Ions change how many valence electrons there are. And in fact, it can change what the valence electrons are in the first place. If I strip away an entire N level, I get a very, very interesting result. So let's look at this really quickly. We're going to do that on this screen right here. So I just want to look at lithium for now. So let me get rid of all this. Oops. I didn't realize there was another layer. There we go. Okay. So we can write out that electron configuration, no problem. What if I wrote the electron configuration for this? Well, then it'd just be this, right? Because we get rid of the valence electron. Which I should actually put a box around because we've been underlining core electrons. So when I do Z effective now, for regular old lithium, it's still 3 plus minus the 2 valence electrons, which gives us the result we would expect. But for lithium, these are now the new valence electrons. And as a result, when I do calculations for Z effective, there are no core electrons. And this is the result that I get. So, which will be smaller? Well, there's 2 effects that are actually making this work. So if I do my little chart here, this is lower. So lower N is smaller atom. And this is bigger. The effect is that both of these multiply together to make an incredibly... Regular old lithium has a radius of 152 picometers. But when I remove just one electron, everything else shrinks down to 60. It's almost 2.5 times smaller. With beryllium, it's even more exaggerated. I go from 112 to 31 by removing its 2 valence electrons because those 2 remaining 1s2 electrons feel an effective nuclear charge of +4, as opposed to the +2 that the outer electrons feel in neutral beryllium. So the end result is that cations are always smaller. If you strip away the entirety of a valence shell, the next layer down becomes the valence shell, and there's that many fewer core electrons, so Z effective for those electrons is way bigger. Not to mention you have reduced N, and reducing N always results in a smaller atom. So if we go back over here, you can see that on the other diagram down there too. So for sodium and magnesium, the effect is the same. Oops. And the reason that the effect is so stark is because both Z effective and N come into play. I've reduced N by 1, and I've made Z effective bigger by making the previous layer of core electrons is now the new valence electron layer, and that's what we're examining when we determine Z effective. Now, if we go in the opposite direction, what do you think will happen? Well, if removing electrons makes things smaller, adding electrons should make them bigger, right? And it totally does. But if we do our calculations for Z effective and N, we get a weird result. And so we'll just do this just to show it. So I'm going to do F and F minus. So these are both 2. But if I calculate Z effective, I get the same result. And you'll be like, what? What am I supposed to do? They're clearly not the same size. So how do we reconcile this? And the answer is we're going to have to add a third column. And this third column is going to be kind of a well-duh column, which I could answer without actually doing this. So here's our third column. And the question I'm going to have for you is, okay, if I have the same Z effective pulling on 7 electrons versus 8, which one is going to be able to hold on to them more effectively? To answer this question, I'm going to give you an analogy, but I'm going to make it a more stark analogy, I guess. Let's say you go to the park and you have one dog that you're watching. And you don't want the dog to run too far away, right? Because if it runs off, then you have to chase it, and that's obnoxious. Okay. So it's going to require your attention, but you can follow the dog and you can shout its name, and the dog will come back to you. Now imagine you had 8 dogs. How much harder is it to keep all 8 dogs close to you by just shouting their names out? Hey, Scruffy, no. Sparky, no. Come back here, Mac. Susie, no, don't run away. Like, you can't spread your attention among that many extra dogs, right? Electrons are like dogs for the nucleus. The nucleus is trying to keep them close, but the more of them there are, the further away they get. Now, the real reason is that as I spread this charge over more things, there's less charge to go around. And also, electrons repel, right? So if I add extra electrons, they just need more space, right? So the takeaway here is that if you add electrons, the size goes up a lot. And the reason for that is the nucleus with the same Z effective is spread over more electrons. But the easier and shorter thing to probably remember is, oh, electrons repel. If I have extra electrons in what would be the same region of space, I need more space to accommodate them. They will push each other away, even laterally. So, talking about anions does require us to add that little extra bit in there, because if we make our chart like we've been doing for everything, we hit that oddity. Oh, that's strange. Everything's the same. What do I do? Well, then you just use electron-electron repulsion. This chart that I have right here, this is called the isoelectronic series. Iso means same, and electronic just means electrons. In other words, all of these have the same number of electrons. I have selected a series of atoms that has varying numbers of protons, but all the same number of electrons. So all of them have 18. So if I have sulfur with 16 protons, it would have a charge of 2 minus. If I have calcium with 20 protons, it would have a charge of 2 plus. And you can see the effect of the radius as we remove... I'm sorry, not as we remove. As we add protons to the nucleus. Now, my question for you is that where would argon go, which has 18 protons and 18 electrons? Or can you predict its radius? So take a shot at it. Give me your best guess for your radius. I bet you're going to get it right. So give me a number and type it in the chat. We'll just give your best estimate in picometers. And then we'll go back and look at the chart and we'll see if you got close. I don't know the answer to this. In fact, I don't think I've ever asked this question. It was just something I thought of. I have a number in mind, though. And we'll see if you can guess that number, I guess. So that was the number I was thinking of, was 150 or so. Let's go check. I bet it's going to be right around 150. That's a little lower than I expected, actually. I was going to expect 150. But 100 does fall in between those numbers. No, it doesn't. It totally doesn't. Wait a second. Hold on. Now I don't trust these numbers. Oh, no. Why is everything the worst? Wait, is that argon on the chart? That's ionization energy. That's not what I want. Well, something is wrong with my data here because it should be between those. And it's totally not according to this. So I don't know what to trust now. Let's consult the internet. Let's see if one of my numbers is just wrong here. So radius of argon in picometers. The internet says 188, and now I just don't know anymore. Now I'm just looking at, I'm trying to find another chart here that has this information. So this site says 154, so now I don't know. Oh no, that's argon with a +1 charge. Wow, what can of worms have I opened up? Well, we're about to take a break anyway, so I'm going to have to look into this to see if I can just get better numbers. Maybe this was just not a very good experiment for data, and I've hit some sort of weird exception or something. I don't know. Anyway, the point that I'm trying to convey here is that as you increase the effective, which is what we're doing as we move across the periodic table, the radius goes down. So I'm going to have to look into that. So when we come back, I will hopefully have an answer for you. I guess we'll see if I can find something. I'm on Web Element, so I'm going to just start looking up ionic radii and stuff like that and see if I can get that information for you. But let's take a 10-minute break, and we'll put some more Stardew Valley music on. So I'll see you in a bit. Hi, everybody. So just in case you weren't following the conversation in the chat here, so I was browsing around the internet, and I find this really fascinating, so we'll just talk about it really quickly. Web Elements. So this is what I was looking at, was this page here. So this is Web Elements. This is a really reliable website about just random chemical information. It's like P-Table, but this guy is British and has been doing this forever. It's the same person that made the Orbitron site that I showed you the other week. So he has a chart here of various radii, and you can see that there's like 75 different ways to calculate this. None of which are 150, which surprised me. And what I suspect is actually going on here is that this chart, with all of my chicken scratch all over it, let me erase all this, is using a different numbering set than this chart, because these numbers I was able to find for different elements. So these are all ionic radii, except for argon, which isn't an ion down there. And I wrote 183 picometers because I found a van der Waals radius, and that sort of fit in here. Like, I don't know. So the short answer is that, I seem to have hit something that I am unsure of for this. So this is what happens when I make test questions or example questions on the fly, is I hit exceptions. So I don't know if I hit an exception or if I just don't know which radius is being used here. But the general gist of what we're saying is true here, is that as Z effective increases, radii go down. And that's really what I care about. So their definition of radius will depend on. Let me put this back up on the screen because I typed this in the chat too. So, and I still have it highlighted. Look at that. So, in the highlighted region up there where it's in blue, the term ionic radius is not particularly helpful, because although its use is widespread. The problem is its meaning, which is clearly very different in some different sources and books. Two values are given here. I didn't type this because I ran out of characters. One is based on calculations, so like we use a formula. The other is based on observations. So in other words, we use spectrometry, or like we analyze it using IR or Raman spectroscopy, which we don't talk about in this class, and so on. And you could click on these links for further details. So I'm going to just paste this in the chat in case, because you guys can just do whatever you want to. You could just ignore it if you don't care. But if you want to click on like all of these different things, you could find out, oh, how are these radii calculated? And then maybe you'll discover something interesting. I don't know. But for the purposes of this class, what I care about is that we just follow these trends that I'm setting out here. So first look at N, and then look at Z effective. Higher N makes a bigger atom. Higher Z effective, if the N's are the same, makes a smaller atom. That's good enough for me. All right, so what I want you to do is I want you to draw out your little charts and use quantum mechanics to explain which atom in each pair is smaller. So, specifically smaller for these instances. Okay, so go ahead and do that. I'm going to give you 5 minutes to do all of these. I'll just number them. And then we'll go over the answers together in 5 minutes. So, see you in a bit. Let's do 1 or 2 more minutes and we'll go over the answers. All right, we'll go over the answers now, and I'll stop talking about my scheduling. There is a bug on my screen right here. I'm just gonna draw where the bug is going. Oh, I drew on him, and he fell off the monitor. He got scared. He's a little teeny tiny bug. So let's go over here. We're gonna make a bunch of these charts. Are there anything on campus for fall? Actually, my understanding is that nearly everything is going to be on campus, except for, I think, a bunch of 161s. Mark is doing live stream. But I believe that they're all hybrids. I haven't looked at the overall schedule. I'm not sure if that's published yet. But the intent is that we're doing at least we're just live stream everything. So, sorry, I'm stretching here. In the fall, I believe that every class will have its lab component on campus, so we'll all be on campus for labs. All of my classes are scheduled to be in person, as far as I'm aware, but I'm only teaching 140 and 121 next quarter or in the fall. So let's do this. So we'll go N max Z effective. Oops. I'm gonna just copy and paste that because I'm gonna use this a bunch. Copy, paste. And we'll just have an extra one over here. Okay. So let's do this first one. So we got magnesium and calcium. And so if I write out the electron configuration for magnesium, that would be... Oh, I need a periodic table. I don't have this memorized. What am I doing? Where can I put this? We'll put it right here. See if this can stay standing up. So magnesium would be neon 3s2, and calcium would be argon 4s2. So for valence electrons, magnesium would be 3, and calcium would be 4, and we don't really need to go any further than this, but if you did this calculation, you should get that. And then you go, okay, what are we doing? We're doing smaller? Okay. So smaller n equals smaller atom. Oh, and that little bug's back. We'll see if I can shoot him away. So magnesium should be smaller than calcium, and it is. All right, we can do chlorine and argon. And for chlorine, we've got neon 3s2, 3p5. And argon is 3s2, 3p6 with a neon core as well. So same N max, they're both 3. So we got to go to the next column. So we calculate Z effective. And you should get, so there are 10 electrons in neon, 17 protons, 17 minus 10 is 7. And then 18 total protons for argon minus the 10 in neon, so that'd be 8. And you say, okay, I want the smaller one, so I want the bigger Z effective, so that's this one. So bigger Z effective equals smaller atom. I should do this to make it clear. There you go. And then we'll go down here, and I'll just go boop. We'll just paste this guy in here. And then for the last one, we got sulfur and oxygen. I'll just do this over here this time. So sulfur is neon 3s2, 3p4. I think that's right, yeah. And oxygen, we'll just do this. And so something obvious thing. Da 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 da. And if you want to calculate it, you can. And there you go. All right. Those are the types of questions you're going to see on the exam. Or the quiz, whenever we get to the quiz on Chapter 3. All right, let's do the next part. So now we'll do calcium and calcium 2+. So if I do this, we get that. And if I do calcium 2+, I get regular old argon, which I should probably just write out like this. Which we'll just do this, just in case. So we could say, okay, well, N for calcium is 4, but N for calcium 2+ is 3. And then if I do Z effective, this will just be 2. But then Z effective for these, oops, let's different color that. Z effective for my new valence layer right here will be 20 minus 10 equals 10. Which is way more. So both of these factors together say that calcium 2+ is smaller. All right. For iodine, if I do the chart for iodine, we're going to get all the same numbers. So I'm just going to write it like this. I versus I minus. We'll just circle this one as smaller. And we'll say same N and Z effective, but less electrons for less electron-electron repulsion. Because in I minus, I have that extra electron, and the extra electron causes more repulsion, which increases its size. That way I can just save some space, because I'm going to run out of space in a second. And then we'll do the last one here. So looking at argon and Cl minus, you should probably just look at that and go, oh, okay, it's argon because its Z effective is bigger. And that's correct. So, oops, I forgot the brackets. In fact, if I write out these, what you're going to notice is, they're the same. Because this should be 3p5, but the little minus there makes it 3p6. So I have the exact same electrons. So what's the difference here? Well, they both have the same N max. But they have different Z effectives, right? And so which one's smaller? Well, it's going to be the one that's pulled in tighter. Because more protons pulling on less electrons. Or not less electrons, but more protons pulling on the same number of electrons as the other case. All right. There you go. That's ionic size. Now, when we move on to ionization energy, these rules are all the same. It's just that the application that we are doing is a little bit different. So let's talk about what ionization energy is. So this is going to require us to go back to those slides that I talked about for hydrogen and helium in a second. But what we're going to do is we actually want to go over here again. And this is going to bring up a question that somebody asked me about the lab, actually. Or not the lab, actually. Somebody in the Discord asked me about some homework questions that were along the lines of, how do I compute the energy of, we'll just get rid of this, an electron. And so I actually need to make this a little smaller. I'm going to draw a line right here. This line represents n equals infinity. If I have an electron on n equals infinity, it effectively doesn't see the nucleus. And as a result, the energy of this electron relative to the nucleus would be 0. And energy is measured in joules, so I'm going to write joules. In other words, if I use Coulomb's law, R is such a large number that E becomes 0. Now, mathematically, this would have to be R equals infinity. That's not possible, right? But because we're working with such tiny numbers anyway, if you get to some distance R, you get effectively 0. So that distance is going to be wherever n equals infinity functionally is. Okay, so that's easy enough to conceptualize. We'll just get rid of that for now. What we're going to do is let's get rid of these electrons real quick, because we're going to draw electrons in our diagram. I should have just erased everything and redrawn that, but that's okay. Okay. So in our diagram, if I have my electrons in my orbitals, so we'll just draw a bunch in here. So let's suppose that we're looking at sodium. Here's what sodium would look like. If I want to ionize sodium, which means that I want to do this to it, I need to remove an electron. That's going to require me to input energy into it, right? Because these electrons are all attracted to the nucleus, right? Which means that the energy of these right here, since it's an attraction, these would be negative numbers. So I don't know, like say 100 kilojoules or whatever. And maybe this is like minus 175. I don't know, I'm just making up numbers here. I don't know what these numbers are, but they're documented and you can find them. The ionization energy, or IE, would be the energy to remove an electron. In other words, I want to take this electron, and I want him to be up here now. How much energy do I need to do that? Will it be final minus initial, or 0 minus negative 100? And if these are in kilojoules, then this will be my answer. This is how much energy it takes for me to promote this electron up to n equals infinity. If I add this much energy, I remove the electron. It's gone. And I have to provide energy for that. You can think of this as me like, if I lift an object off of the table and up like above my head, I have to import energy into doing that, right? I spend energy to lift the object. We are essentially lifting electrons up out of the nucleus. And so that's what ionization energy is. Now, when I do this, I change the effective, I change the radius, all the rest of these would get closer. And thus, the next electron that I pull is harder to do. So the second ionization energy will be harder than the first one. And the third one will be harder than that. and so on and so forth. So as I remove electrons from a given atom, I have to pay energy to do it, and then pulling away the next electron is harder. Now, when I am doing this, we'll clear all this stuff out again. And this too, this can go away. Your ionization energy is going to depend on two factors. One is the distance, because remember, Coulomb's law cares about this. If R is bigger, in other words, the electron is farther away from the nucleus, there's a lower energy holding it in place. So, less energy needed to ionize. That checks out, right? If my electron was way up here and I only had to move it this far, that's less energy, right? So, that's straightforward enough. Okay, let's look at the other case here. Oops, what have I done? I've selected all. I don't want to select all. I want to just get rid of this. Okay. The other thing that I'm fighting against is I'm fighting against the nucleus, right? So the nucleus's effect is Z effective. If Z effective is low, then there is less attraction to the electron, and it's easier to remove. So the takeaway here is that ionization energy depends on N and Z effective, and bigger N makes it easier, lower ionization energy, and smaller Z effective makes lower ionization energy as well. So it's sort of like we're inverting radius. And it's tricky to keep all this in your head, but remember from the perspective of Coulomb's law. Just keep this formula in your head. Even though we never use this formula, everything follows it, right? It's all about attraction to the nucleus. And so if I want to make E as small as possible, I either make R huge or I make Q tiny, right? Where Q1 is charge and Q2 is the other charge. So if I make this the nucleus and I make this the electron's always going to be the electron, right? But I can make the nucleus's effect, or Z effective, as small as possible to minimize E. That's basically ionization energy. So let's just go through a bunch of examples now. So the first example I want to do is I want to go back up to here, to the slides that we skipped. Here are my ionization energies for hydrogen and helium. And I want to look at these in more detail. And let's see if we can explain them. It takes 1,312 kilojoules to remove an electron from hydrogen. But it takes almost 4 times as much to get the electron off of helium. And so let's try and figure out why that is. All right. And we'll go over to this one to explain that. Oh, I have like 74 layers. Hold on. Let's merge all these layers. And then we'll erase all the layers, and then everything's great. Okay. I don't want to write that. I want to write this. And so we're going to do this again. And we're going to just put this over here. So we know that for both of these, n is just 1, because we're dealing with 1s, right? It's only n equals 1. And if I calculate z effective, there are no core electrons, so it's just whatever z is. Now, if I look at this in terms of radius, we know that helium is smaller than hydrogen. So for helium, it's going to have a smaller radius. So if I do r or something, we'll say some number and then some smaller number. So z effective does have sort of a double effect on this. But importantly, z effective is going to be one of our charges, right? Well, if I double the charge, this number should double, right? And if I make this number smaller, this will go up proportionately. So as a result, when I compare these two numbers, we would expect this number to be bigger. Because removing an electron from something that's pulling on it with a force of 2 plus is going to be harder than removing an electron that's being pulled on with a force of 1 plus. And furthermore, the electrons for helium are closer to the nucleus than those of hydrogen. So that's going to make it harder too. So both of those facts together help us explain that, oh, it's harder to ionize helium. In fact, it's extremely hard to ionize helium. All right, so we got that example. That checks out. Let's go back to where we were, which was here. There we go. All right. You'll notice that I was writing this number right here, i.e. with a little 1. That's because there's nothing stopping you from taking more electrons. You can take as many as you want. Now, ionization energy has to be a positive number. And the reason for that is if we go back over to this diagram, helium has that number listed as the second ionization. Oh, interesting. What does it have listed for the first ionization? It should probably be the same as the hydrogen, but doubled and then slightly bigger, I would say. So if my number was, what did I write down? 1312, I would guess like 2800 or 3000 for helium for the first one. All of these numbers that I get, by the way, are out of textbooks, so I'm always surprised to find that they're mistakes. So 2300, that's about what I would expect. Okay, cool. So what was I talking about? I wanted to go over here and go onto this screen. All right. Now, because ionization is this process right here, us lifting an electron up, we always have to put energy in to do that. If ionization energy was negative, electrons would ionize on their own. Our electrons would just be like, whee, goodbye, and they would disappear. So all atoms have positive ionization energies. Now, the ionization energy for some atoms might be rather low. And the reason for that would be if we're pulling something from, say, like n equals 6 or whatever, there's just not that much difference between n equals infinity and n equals 6 in terms of its energy. So some atoms will have very low ionization energies, and as a result, they're very reactive, but they will never be 0, and they will never be negative. All right. Here's a chart with ionization energies on it, and our job is to explain the chart. Now, what are the things that we're going to use? We're going to use N and Z effective. Oh, there's your 2300. Look at that. So I might have to go back and edit that number. Okay, that's interesting to know. So what do we notice about this chart? Well, we notice that when we go from n equals 1 to n equals 2, we're going to pretend that didn't happen there. There's this huge drop in ionization energy. And then stuff starts to go up. And why is that? Well, it's our friend Z effective. So let's go explain all these effects and see what we can observe. All right, I'm going to just put this much of the chart on here because that's what I can really fit. But let's clear everything. So boop. So here's our chart. We need n equals infinity, so we'll put that back in there. I need this, though, so that you can actually see it. All right, so if I have an electron for lithium right here, here would be my ionization energy for lithium. So this would be IE for lithium versus an ionization energy for helium. And you can see that this distance here, my diagram is a little exaggerated, obviously. Like 2s is way closer to 1s than it really is. But you can see the length of the line that I'm pulling the electron for where helium's last electron would be is longer than the length of the line for lithium. So helium's ionization energy should be larger than that of lithium. And it totally is if I could fit it on the damn chart. I'm just going to make this smaller. There we go. So that checks out. Okay, let's get rid of helium here. Undo, undo, undo. 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 There we go. Oh, I gotta undo one more time. Boop, there we go. So that makes sense. Now, what about for beryllium? If I add an extra electron, what's pulling beryllium closer to the nucleus? Well, for lithium, Z effective is 1 plus. So I have a 1 plus pulling the electron away from my ionization energy effort. But for beryllium, Z effective is 2 plus. So that would be a 2 for beryllium, which means that I have to pull harder. So the ionization energy for beryllium should be higher than lithium. And you can see on my little diagram up here, it totally is. So we've got, here's lithium, here's beryllium right here. And it's almost double, right? So it's like about 500 versus about 1,000. So that checks out. Now, here's something odd. Why is the next ionization energy lower for boron? Well, let's go put in the next electron for boron. Where does the electron go? Well, here's boron. It's right here. What happens? Well, boron's slightly less, so it's easier to ionize despite there being a 3 plus in the middle because we're pulling from a 2p orbital, and we know that 2p orbitals are lower in energy, or I'm sorry, 2p orbitals are higher in energy. I wrote the wrong symbol. Than 2s. Right? Because the order of energy in orbitals is s is the lowest, then p, then d, then f. So therefore, it's slightly easier to pull an electron away from a p orbital. So that's why there's that little drop there. And then for the next few elements, well, I'm just fighting Z effective. Everything else is the same, so it increases again. And then we get to oxygen. So let's just write these in here. So boron, carbon, nitrogen, oxygen. Why is oxygen the next thing to drop? Because we aren't entering into an orbital, like the next orbital, so there's not a different thing here. And Z effective is increasing. So what happens with between nitrogen and oxygen? And the answer is, here's where my next electron goes. What's going on here? I have electron-electron repulsion. When I force my electrons to be in the same orbital, and then I say, hey, I'm going to remove one of you, what does the other electron do? He pushes him out. Sweet, I never wanted a second electron in my orbital because we repel. So as a result, oxygen's electron-electron repulsion by the paired orbital in that 2p orbital there causes the ionization energy to be slightly less than we would expect. So in other words, if I go back to this diagram right here, if there was no electron-electron repulsion, this is what the chart would look like. It'd be something like this. And so these numbers would be like this for the next three elements. But electrons do repel each other, and so they provide this much of a boost to our efforts into ionizing them. And it just turns out that that makes there be a drop between nitrogen and oxygen. So everything is slightly lower than it should be due to that. So to summarize our observations on this chart, let's just write these up here. So as you increase N, ionization energy is lower because the electrons are further away. It's easier to remove them. But within an N, higher Z effective equals higher ionization energy, which we can see is the general trend for our within an N. And then our exceptions, I really don't like writing on green. I realize that that's a problem if you're red-green colorblind. But this just says the word exceptions here. So if you go from S to P, there's a little gap. So this would be S to P. Is this one right here. And then the first time you encounter, I have to write real slow, electron pairing. Oh, for fuck's sake. And that's right here. So here, I go from this to this. And you can see that pattern repeats itself. So here's my S to P. Here's my electron pairing. Here's my S to P. It's sort of across the transition metals. And then here's my electron pairing. Now, the last thing is, oh, look at all these ionization energies for the transition metals. They're all the same, right? Well, why were all the radii the same for transition metals? Because they have the same Z effective and same radius. Similar ionization energy. I apologize that looks so stupid. Writing on like giant JPEGs apparently makes PowerPoint freak out. All right. There are all of our ionization energy trends. So that's everything that we care about for ionization energy. Wow, we're out of time already. I should have not talked so much about random classes and stuff. All right, but there's our trends on that slide. So the next few slides are just describing that. And then we'll get to the examples. So we'll start with these examples on Thursday. We have how many more topics do we have in quantum mechanics? We have this and electron affinity. And electron affinity is literally the opposite of ionization energy. So that won't take very long to do. And then look at this right here. So you are here. This is the end of quantum mechanics. So we're going to finish it on Thursday, and then the rest of this is just rubbish. We're gonna do all of this on Thursday because it's all this is we're back to 140 again. This is all the common shit that like you already know the answers to. So we're gonna whip through all that. We're gonna finish chapter 3 on Thursday. Thank fucking Thor, right? Like we're so sick of chapter 3. I don't know about you. I'm sick of chapter 3, so we'll come back to that when we have class on Thursday. So I do want to thank everyone for coming out to the lecture. Make sure that you ask me questions about chapter 3 because again, yeah, this stuff is ridiculous. I know it's difficult. But do the best you can. I think that we're doing okay. Based on feedback I'm seeing in the chat, I think it's going pretty good. Obviously, I'm speaking for like 2 or 3 people. There are 50 of you in the class, so please, please, please ask me questions. Let me know if you need anything. Lab number 3 is due on Wednesday the 18th. It'll close on Thursday. Go out and enjoy the sun, because it's going to come out this week. Cheers.